Hey, it's Aaliyah from Elia's Electronics, and today I'm going to do the first video in the microcontroller tutorial series, and we're going to talk about GPIO. Now, what is GPIO? GPIO stands for General Purpose Input-Output, and basically most of the pins on a microcontroller are GPIO pins. Now, you can connect all sorts of stuff to it. You can connect buttons and LEDs and more complex things like also chips, other ICs, so you can communicate with them. And what the GPIO pins allow you to do is acquire data in a simple binary form, or actually send out data in binary, by ones and zeros, setting it to the supply voltage or pulling it down to ground. Now, for this purpose, the basic circuit looks like this. So we've got our voltage regulator here that creates our 5 volts regulated power supply, which is called VDD here. It could be any operating voltage that the microcontroller can work with. It could be 3.3 volts as well. And the circuit looks like this. So we have got our microcontroller here. The VDD pin is directly connected to our supply voltage. The master clear pin, which is the reset pin, is connected to the supply voltage via a 10 kilo ohm pull-up resistor. Now that is needed so that the PIC doesn't accidentally reset while it's working. We don't want it to reset by accident by some random noise that is present at this pin. So it generally is a bad idea to leave this pin floating if it's activated. You can actually enable or disable this in the configuration bits, but generally I always put a 10K resistor there, and I've got it always enabled, so just so it's stable at VDD and doesn't reset. Now then it's connected to ground via the ground pin, and so then we've got one GPIO pin connected to an LED by a 1K current limiting resistor. Now this is important because the microcontroller pin can only supply a certain amount of current. In PICs, that typically is about 20 milliamps per pin, but you shouldn't really draw 20 milliamps. You should keep below that. So GPIO pins are very low power pins. You can't switch a great load with it. If you were to switch multiple LEDs, then you probably should use a transistor to switch the LEDs, because the more LEDs you got, the more current you need, and as I said, the pin can only supply a certain amount of current to the load. Now, on another pin, we've connected a switch. Now that switch is switching this pin to ground when it's pressed. And now you have to connect the switch, or the pin. You have to connect it to your supply voltage too via a pull-up resistor, and that basically is done because you want to have a steady voltage on that pin. So when you read in the pin, or you read the pin level, you always want to read 5 volts, or your supply voltage, as long as the switch isn't pressed. If you don't put this resistor in there, then what is going to happen is the noise, just noise that it picks up, like the 50 Hertz mains hum, is going to be present on that pin, and then the pin could go low, although the button is not pressed. So now, how do we tell our microcontroller which pin is an input or an output, and which level it's supposed to have, or how do we read a pin level from an input pin. Now, for that purpose, the PICs have got 3 registers. The 3 registers are the TRIS register, which is the data direction register. It defines which pin, if the pin is an input or an output. So if the TRIS bit is set, then the pin is an input, and if it is cleared, so if it is 0, then it's an output. You can kind of remember that scheme by, if it's a 1 kind of looks like an I, so it's an input, and 0 looks like an O, so it's an output. That's how you can remember which TRIS, how you have to set the bit in the TRIS register. Now the LAT register, that's the output latch register. And the output latch register defines the output level of a pin when the pin is an output. So when the LAT, a bit in this register is set, then the output pin is going to be high, and if it's low, if the bit is cleared, so if it's 0, then the output is going to be low. So it's going to be connected either to the supply voltage, or if it's set, or to ground if it's cleared. And then for inputs, for reading the input levels of a pin, you've got the port register. It basically, you know, if there's VDD present on the pin, then it is going to be 1 in that register, and if the level is low, i.e. ground, then the bit in that register is going to be 0. If the port is configured, the pin is configured as an output, then this register is going to define the output state. However, the port register is going to reflect, also going to reflect the pin level. So if you've set it to an output, and if you've set the output high via the latch register, then in the port register there's going to be a 1, 2 in the at the corresponding pin. So I've got a little table here. If the direction bit is set to 1, means we've got an input, and now the latch register is not used for the input pins, so it doesn't matter what the latch register does, because this pin is configured as an input, so the output latch is disabled. Now, if we have got VDD present on an input, then the port, the corresponding bit in the port register is going to be set. And if we've got ground present, then the corresponding bit in the port register is going to be cleared. Now, if we, on the other hand, have a 0 in the TRIS register, which means that the pin is configured as an output, then we, depending on how the latch register bit is set, the output is going to change. So if we've got a 1 in that latch register, then the pin is going to be at VDD, and if we've got a 0 in that latch register, the pin is going to be at ground level. And as I said, the port register also reflects, this basically reflects the state of the latch register in this case. Now, when you connect a switch to the microcontroller, then, you know, in this schematic, it looks very simple, and but it isn't actually that simple in real life. It's not that simple just putting a switch on the pin and assuming that there's going to be a clear transition from a high level to a low level. So ideally, what you want to see on a switch, on the switch we have up here, is that as long as the switch is not pressed, the voltage is at 5 volts, which is our VDD. And as soon as we press the switch, the voltage is going to immediately ramp down to ground level, and it's going to stay there until we release the switch, and then it's going to shoot up again. Now, that's the ideal case, but because switches are mechanical devices, the switch contacts, when you press them or release them, they are going to bounce a little, and then you get very high frequency noise on there. So in practice, it would actually look something like this. This gray line here shows the actual voltage. So you can see, you got that kind of ripple when you press it, and then it might actually, for a short time, lose contact and go above the switching threshold again, and then go to a low level. So this switching threshold means that that's what the microcontroller, as soon as the voltage is above that threshold, the microcontroller interprets the pin to be high or low, depending if it's over or under that switching threshold. Now, again, as I said, this could, just bounce around below and then go above and then again go below that switching threshold, and the same on the if you release it. So the orange waveform is actually what would result for the microcontroller. Now the microcontroller in this case, if we want to detect the falling edge, then we would actually have 2 falling edges in this case, and we would also have 2 rising edges in this case. So that really is not good, because this would result in an unpredictable amount of button presses. So the microcontroller might think we've pressed the button 4 times, but we actually have only pushed it once. So what you have to do is called debouncing. And debouncing can be done in different ways. It can be done in software, by a software filter, or having a timer that fires on a falling edge, so when it goes from high to low, and then it waits a certain amount of time, and waits for this switch to settle and to stop bouncing, and then take another reading. And if it's low, it knows, if after a certain amount of time the pin is still low, then it knows the button has actually been pressed. If it's high again, then it knows that, it's not being pressed, or that it has been pressed for a amount of time that is too short. So by by checking maybe here what the pin state is, you could determine whether the button has been pushed or not. There's another method. It's more of an analog method here. It's called, you can do it in hardware. So you can use an RC low-pass filter. So you still got your switch here that's switching to ground, and your pull-up resistor to VDD. But also you've got this RC network, this RC filter. And what this, a low-pass filter in this case, and what this does, it, as the name implies, a low-pass filter, it passes all the low frequencies, but it filters out all the high frequencies. Now so what will happen is this noise is going to be filtered out, and you get more of a clean transition from high to low. So you get it more to look like this waveform here. You might have seen this formula before. That's the formula for the cutoff frequency of an RC filter. It's 1 over 2 pi RC. So if we want to calculate the capacitance, the formula would be 1 over 2 pi times R times the cutoff frequency. Now let's say we want a cutoff frequency of 4 Hertz. So that means that we could detect button presses at up to 250 milliseconds. So every 250 milliseconds the button could be pressed and it would be detected as a single button press. But all this, the noise, the settling time or the bouncing of the switch, which is much higher frequency in the hundreds of hertz, is not going to be interpreted as a switch press. Now let's say we make R a 100 kilo ohm resistor, which is 1 times 10 to the 5, times 4 Hertz. Then we would get a capacitance value of about 400 nanofarads. So if we would put 100K here and a 400 nanofarad capacitor here, then we would be able to detect 4 button presses per second. So a button press every 250 milliseconds, and everything above is going to be filtered out. Okay, so now let's look at the software. I've set up all the, I've set up the IDE in the way we need. I'm going to upload all the code to GitHub, so you will be able to download the source files and the project files. So we know that our LED is connected to RC5 and our button is connected to RB6. So that's the button and it's an input. And RC5 is our LED and that's an output. So, and because it's on RC5, the corresponding registers for that are TRISC, LATC, and port C, of which port C we won't be using. So in the TRISC register, what you can do in the MPLAB IDE, because of the header file, you can say TRISC bits, and then you get a selection of which bit you want to actually modify. It's an easier way and it's easier to see notation. And we want to set this to be 0 because we want it to be an output. The alternative way of doing this will be TRISC and then setting it like so. Setting the a 1, shifting a 1 into the TRISC register by 5 because we're on TRISC 5. Also, that would be the same as ORing the TRISC register with the hex value of OX40, which will result in the same thing. I'm sorry, actually inverting that, so like that, because we want to clear the bit, not set it. Now the next thing we want to do is in the LAT register, in the LAT-C register, we want to start the LED, we want to start off by the LED being not lit. So we want LAT-C bits and then LAT-C5 to be 0, 2 because it's low. Right? That's the pin low, and this is pin's output. Now on the RB6 on the other hand, we want to configure it as an input. Now, therefore, we have to, in the TRISC bits register, we have to set RB6 to 1 to have it as an input. And then we, sometimes what we have to do is, because these inputs are also sometimes multiplexed with the ADC, we might have to enable the digital input buffer, and we can look that up in the device data sheet. So right here we're in the I/O port section of the data sheet, and I'm going to jump to port B, and well, actually we have to go a little bit further down here, which is the port analog control. Now what this does is the ANCEL and the ANCEL high or H register, they control if an input is either a digital or an analog input. And by default, these bits are all set to 1. So as you can see, the digital input buffer is disabled. So that means that you can't use them as a digital input. You will have to set the corresponding bit in these registers to 0 so that that you can use them as a digital input. Now luckily in our case RB6 is not an analog input, as we can see from here, so we don't have to do that. And the rest is pretty simple. Now in our while loop, because we want to do it over and over again, we just say if, oh wait, let's see, even easier in there. If the port B register has the RB6 bit set, right? That means that the, cleared, because it's a low active switch. Then the button has been pressed. So we're going to say if port B bits dot RB6 equals 0. So if RB6 is cleared in port B, then what we want to do is set our LED pin to high, because we want it to light up. And if that's not the case, then we don't want this to happen. We want it to be 0, not to be lit. So that's the basic software, and we can compile that by hitting this button. Let's see if we don't get any errors. We shouldn't get. Alright, we're not getting any errors. So here we've got the microcontroller. That's where the button is, and the LED that's going to light up is this one. So when I press the button here, if I can manage to press it, then you can see that the LED lights up as long as I press the button. Now note that I'm not using any debouncing here, because this is such a simple task that we don't need any debouncing, because we're not counting the number of button presses. It's not important how often a button is pressed. But if you want to navigate through a menu or have a user menu or something and want to count the number of button presses, then you would have to use debouncing. And of course this is just a simple task to demonstrate how to read an input and generate an output. Of course this is not a really useful task for a microcontroller, because just connect the LED to the switch if you want to switch it on. But I hope this video was helpful in explaining how GPIO pins on a PIC microcontroller work, and please give it a thumbs up and subscribe if you like it, and I'm going to continue doing these videos.